welcome to the third session of the Founders Day presentation. A couple of announcements before we get going. If there are any EGR 300 students, there's a sign-up sheet that you should sign up on when you get done here. So that was a requirement for you. Dr. Bijli is handling that. And the second one is about our senior lunch, which is going to be on May 1st. This is for graduating seniors, and if you've not responded to my email yet, let me know after the session. I'll put you down on this, okay? May 1st. All right, with great pleasure. As you can see, it's this team. Actually, I have a public apology to make. There are people listed on the program, and you see 4 presenters. The problem is one person's name does not appear because of my fault. I'll take the blame for it. Mr. Nathan Chimeniki, I'm really sorry. I left it out when I gave that information to Jamie Struhecker, who was putting together the whole program. So you can write it down when we start. And also, you might have noticed that they have actually switched these presentations. So the force sensing treadmill will go first, and then the wear testing of knee implant will go second.
All right, thank you everyone for being here today. We have the Force Sensing Treadmill for Biomechanics group. I'm Will Schlofeld. Right here we have Timothy Anderson, Mitchell Stricker, and Nathan Schmidt. All right, so a quick overview. So we're going to talk about the background, kind of the prompt for this project, the problem that Dr. Monroe wanted us to address, the solution we ended up coming to, the design iterations that we went to get to this point. We're going to demonstrate some testing. We're going to talk about some future improvements that we recommend for the product. All right, so some quick background. Mitchell's going to talk a little bit more about this product, but the problem. But Dr. Monroe has a biomechanics lab that she does for a senior technical elective. It's going to be expanded into a master's level course. And so she wanted us to overhaul and create a force sensing treadmill that would kind of address some certain problems that she had with the current force plates that she uses in her lab setting. She kind of wanted to be able to measure a person's gait over a longer period of time. And the reason this is kind of important is because it helps better understand the forces and kind of the impact that the forces go up through the joints for physical therapy, rehabilitation, as well as for implants. We worked with Vernier Sensors as our industry advisor. Dr. John Melville and Dr. Monroe they're a sensing company here in Portland, and Dr. Monroe had some credit through winning a competition with them, and that will kind of factor into part of our budget.
Okay, so Dr. Monroe's lab right now is it's in her biomechanics lab. She has a force plate that sits on the ground, and someone either walks or runs across it to measure the force that's going through the person's leg. There's a lot of limitations that come with this type of setup. One of them being that when someone walks towards an object, they usually use that object as a target, especially when they're told to step on this object. They're going to try and heavily make their step, I guess, as perfect as possible. So you don't get the best results. So one of the reasons why she wanted a continuous force sensing solution is, as someone walks over a period of time, they tend to forget what they're walking on, when it comes to these force plates, so that they can steady their gait, and then we can get a better measure of that type of force. The other problem that comes with these force sensing treadmills is that most of them are heavily expensive. We got some figures from around $60,000 to $120,000 that these force sensing treadmills can run from, and they have a bunch of stuff that they can do, but obviously we don't have the money to buy one of those, so Dr. Monroe had us build one for, I think we got it under $1,000 or something like that, so yeah. And that's the solution we were able to get, was this thing you see right here, which we will show you guys how it works. It's a force sensing treadmill that utilizes Vernier force plates to detect force as someone walks or runs over it. Some of the design criteria that we had to really focus on included one that she wanted it to be continuous force sensing. She also wanted it to be a treadmill design that was safe for users. So we didn't want to take any of the safety features that are built into the treadmill. She wanted something that was a treadmill because a lot of people know what that is. They've used one before, so it's easy to pick up, plug and play type of scenario. And then we had a budget of $2,300, $1,000 of it being Vernier software, and then $1,300 of it being money that we can use on anything.
Alrighty, so I'm going to talk about some of the design iterations we went through in creating this project. This cube I've got here was our first iteration. Nathan will pass it around. We call it our strain cube because it was a steel cube that utilized strain gauges mounted all over it. And strain gauges are essentially a very long wire that, with the current passing through it, has some kind of resistance. And when you attach it to an object and then deflect that object or apply a strain to it, the length of the wire changes and therefore the resistance as well. So if you hook a strain gauge up to a circuit called a Wheatstone bridge, you can actually measure that change in resistance. And the way this works is you have 4 resistors of equal resistance, and when a voltage is applied across this bridge, you can probe this point right here, and when the resistance, or when all the resistors are balanced, the voltage reads 0. And then if you apply a strain to whatever object your strain gauge is mounted on, you'll detect some sort of voltage change across here. So that was our idea because we wanted to create some sort of sensor that could measure forces applied in 3 directions that we could then mount within the treadmill. Unfortunately, our steel cube was much too strong to work with strain gauges. We weren't getting voltage values that were usable in any way. Even with heavy amplification circuits, we just got a lot of noise, and in the end it wasn't really a viable solution. So we decided to ditch the 3 axes of force sensing and just target a single normal axis that we knew would work through the use of these linear force plates. So that brought us to our second semester. We were donated a treadmill, a non-working treadmill, had no belt, the motor wasn't even running, but we used it sort of as a mock-up proof of concept for idea of using force plates and these force tables mounted within the treadmill frame. And the purpose of these tables was to isolate the force plates from the frame itself. We didn't want to mount the force plates within the frame due to some vibration issues we thought we'd encountered. So this was our method of getting a direct path between a user's foot, a force plate, and then the frame. So after we had confidence in this basic wooden mock-up, we bought a treadmill and fabricated some parts into what you see today. It's a little difficult to tell in this picture, but you can see there's 3 force tables within that treadmill housing 3 vernier force plates, so that when a user walks on the treadmill, their foot will land on the first plate, slide across the back, and then they'll push off on the last plate. And there's some really interesting things we can do with that. So again, this is some pictures of our final design. Over on the right here, we have our steel table with vernier force plate mounted to it. And it's just a polycarbonate top sheet that ends up mounting flush with the running surface of the treadmill. And here you can see we put some slack in the belt and lifted it up, and we have our 3 force plates mounted front to back with a hole cut out of the treadmill's original running surface.
All right, so along the way we had to make a lot of decisions on what we were going to do with the design. So the first decision we had to make was, well, will we use force plates which just take a single force, and there's multiple axes, and some of them are 1 axis. The ones we have are vernier force plates, and they have 1 axis, so they just take the normal force. And our budget, we had $1,000 set aside for vernier sensors, and they don't make anything other than the 1 axis. So we thought about trying to maybe buy them and work around and build ourselves a 3-axis force plate, but that was going to be cost prohibitive. So we decided to use the strain gauges. And then after going through all of the first semester and doing a lot of iterations trying to play with that strain cube that Tim talked about, we decided that wouldn't really work, and so we decided eventually to just use those force plates. Once we got that figured out, we had to decide where we're going to put the force plates. We could have mounted them, done a really easy thing and thrown them underneath the treadmill, and that would have allowed us to get a person's force put into the ground, but that's all it would get. It wouldn't allow us to get like a step off, step on, anything like that. And so we decided to do 3 force plates throughout the length of the treadmill. So you step onto one, you pass over another, and you step off of the third, kind of as you're walking. So then we decided we needed to put them inside the treadmill. And in order to do that, we had to make these tables. The tables are relatively simple. The only thing that made it tough was that there's not a lot of space within the belt between the bottom and the top through the deck. So we had to come up with a treadmill model that would allow us to do that. And treadmill models, I mean, they range from about $350 if you go to Big 5 to a couple thousand. But we wanted something that was relatively simple and we could modify, so we went with a cheaper one. Because the more expensive they get, the harder it is to work with them and keep the same traits of the treadmill. So once we got that, we threw the treadmill or the plates in there, and here comes a bunch of rubbing and friction on the bottom side because that space between the plates or the top and the bottom of the belt isn't big enough still. So then we decided we needed to use kind of a trapezoidal tread. So it goes up, and then we put in 2 more conveyor belt rollers down lower that allowed the belt to give enough space in the middle for those plates. And then we had, once everything mechanically was built, we had to decide how we're going to interface that with the computer and actually be able to use our force plates. So we decided to use Logger Pro 3 as our software because that's, one, it's Verniers' main piece of software that all of their equipment interfaces with. And then 2, because that's what Dr. Monroe is used to using in our lab, and that's what she always has used. So we figured something that she's used, she's comfortable with, and her students will be comfortable with because of that would be best. So in that, we built a program that Mitch will talk about now.
Okay, so this is a screen capture of the actual code. We'll show you in a little bit when we do a live demo. But basically what this shows is 4 graphs from these first 3 are the individual force plates being the front, middle, and back of the treadmill. And this last one is called the calculated column, where we just sum these 3 together. So we can get like a general trend of all the force that's occurring in the treadmill at one time. Now we're going to do a live test over here. So this is in real time. As you can see, there's different peaks as well as walking on it, and you can stop it. And so you can see the general trend of the data. These are all lined up. This was a 15-second increment. I just decided to stop it for time. But I'll go back to the other slide so that we can see a little bit closer. This is on a 2-second time interval, whereas the other one was a lot larger, obviously. So what you can see here is when someone takes an initial first step, there's a large peak in the force. We can actually tell what that force is. And then as their foot moves across the second plate, you see it start to grow, and then it dips off as their foot goes over that, and then it peaks right when their foot hits that third plate. And this is when they're stepping off with their other foot to move to the front again. So this can show us a lot of different things, from running to walking to skipping to any type of stuff like that. And it's really helpful because we can see the amount of force as well as where the force is distributed throughout the the stride of the gait, and we can kind of figure out how much force is going through each leg, all that stuff like that. And this calculated column just shows the general trend of where the force is, and we can kind of see where the maximum force is at one point in the treadmill. And then you want to do the next one. So we're gonna really fast show a different type of walking pattern. Will is gonna so he has a little bit of a he's kind of struggling there to walk. But as you can see, the first plate is getting way more force than the other ones are, and it kind of carries through. And by the bottom, it gets smaller. So what's nice about this is you can kind of see as you move down, it moves diagonally along the thing, and then you can see how the force gets larger and smaller as it goes. So that's just another, I guess, iteration or example of what you can do with this software.
All right, so as you listened and watched Will work with the treadmill, you'll notice there are a couple things that weren't quite perfect. The first is that the motor is a very small motor just because it's a cheap treadmill, and that the weak motor has a lot of variance in the amount of torque it's applying as he's going and walking, especially the harder he steps, the more work it has to do to push him backward. So one upgrade would be the treadmill motor, to put in a new one and retrofit that and allow it to have a more smooth, continuous force distribution. Another thing that we would like to do is to add that second and third axis of force, which we tried to do initially, but it proved to be too time consuming and kind of outside of the range of our project to have a working treadmill at the end. We'd also like to maybe on the front of the user face or the user interface, right now all it says is like speed, and it gives you amount of time you've walked on there and maybe heart rate. We'd like to possibly interface an actual monitor onto there, so as you're walking on the treadmill, you can see how much force you're applying at any given time. And then outside of the scope of this particular project, we'd like to find out what you could do with a cheap force sensing solution that maybe is beyond the academic ability. So maybe physical therapy things or athletics. Right now, Nike and Adidas and a lot of the upper division or higher athletic companies do have force sensing treadmills, but like I said earlier, they range of upwards of $100,000. And so having a small startup company with a lot cheaper equipment, that might allow them to become one of those larger companies.
All right, so just to kind of recap, we talked about the background of the problem that Dr. Monroe presented to us. We showed you the solution, kind of multiple iterations we went to get to that point. We demonstrated some testing, and we talked about some future improvements. So we wanted to just go through the acknowledgements. Dr. Deborah Monroe, she sadly couldn't be here today. Dr. Martin Shorten, Biomechanica. Our industry advisor, Dr. John Melville, Vernier. Alan Hansen, shop supervisor. Jacob Amos, shop technician back there. Dr. Heather Dillon, Dr. Khalid Khan, our instructors for senior capstone, and Sorted Engineering faculty and peers for their input, because without all these people, we wouldn't have this treadmill here today. So we would like to open it up to any questions people may have.
Quick interjection. Unfortunately, I have to run to another presentation across campus, so I want to say thank you all for coming, and I will leave the questions to these.
Yeah, what's the resolution on the force plates? You had it on the spreadsheet showing 1 resolution. Assuming it's better than that.
Yeah, we were capturing the data at 60 hertz. I could look up the resolution. I don't remember offhand.
But it's better than the 180.
Yes, it's better than that. Yeah.
And is there variability in choosing sampling?
Yes, actually, we didn't really get into that stuff, but a lot of the Logger Pro software is all this different stuff in there. You can change the sample rate. You can do a lot of like sampling and cutting off high and low frequencies and all that stuff too. So we're still kind of working on that stuff because Monroe's been gone. We haven't been able to work on the lab part with her, but that's kind of what we're going to be doing in the next couple of weeks when we build this lab. Is kind of there's a lot that Logger Pro can do.
There's just one sample lab. There's a lot more options.
What's an example of a kind of force that would have been taught with the cube that's been run around?
So that'll allow us to take lateral forces and forward and back. So say if you're an athlete running, you always want to try to push yourself immediately forward. So it would be able to capture if you're moving left or right with your force, if you're pushing one way or the other because you want to take that straight line, or things like that.
So you guys said that your strain cube was made of steel, and that high strength was maybe prohibiting some of the smaller forces. So I'm assuming other materials were also a consideration early on, and why did that take hold?
One of our biggest considerations is that we wanted it to be a strong enough material that somebody could run on it for an extended period of time.
And still feel comfortable. Because if you have a lot of give in a treadmill, the treadmill might be moving up and down, and it might be strong enough to support them, but a lot of times users, you want to make sure they feel comfortable running on it. So
Kind of tied into the gait part of it. If somebody can't reach that comfortable, natural stride, there's not really much point to it.
Did you run into any problems? You said that you took the original belt system, made a trapezoid out of the seat, fit the force plates in there. Did you run into any problems putting those extra rollers in there just because of the treadmill was already put together? How did you guys overcome that?
Well, so we basically just added brackets on the inside of just the main support beam, so it's housed in there. It actually wasn't too bad. I would say probably on a much more expensive treadmill with a lot more going on, this would have been a lot harder to do. But luckily, yeah, there are these little brackets right here that just roll through. There's actually a decent amount of space there. We were a little nervous that we would run out of room for our force plates, but it actually worked out. Yeah, I mean, it wasn't the worst installation in the world, but yeah, they just kind of sit in brackets that are drilled right through the support beam.
nice thing is that the end belt bracket part has screws, so we were able to unscrew it all the way, give the most slack possible, put the rollers in, and then just tighten it back up.
What process did you go through to actually like decide that you were gonna buy this treadmill? Because I doubt that they let you like take it apart at the store.
So we initially thought that we might be having some treadmills donated to us, working treadmills, and that fell through. But while we were doing that, we figured out a couple that they gave us kind of a couple that might be given to us. And so we found one that was similar enough to those that we could take it, and if this was our first iteration, we could use the same measurements and everything and just go over to the new one. So that was one of the biggest things for selecting this model, beyond how inexpensive it was that it would work with the future iterations.
Kind of set up the force plates and said, okay, they're roughly this width, and if we stack 3 of them, they're roughly this height. So we just kind of examined that and some treadmills.
Dr. Doty, did you have
Any other questions?
So I noticed when you guys had your total force graph down there, it was hanging out around an average of 1,000 newtons, I believe. And it looks like you guys are, I guess, all the steps are kind of getting blended together. Did you guys have any suggestions for like coming up with ways to separate out the steps so you can tell like what the left foot's doing and what the right foot's doing?
based off of what we've done, I mean, you can see peaks in the data, so we know that like the initial, like when the foot first stepped, that's going to be, that peak is where like the maximum force that went through the leg. And then this would be like the step off point. I mean, it's what you'd have to do some analyzing of probably how far the person walks, so you can understand, I guess, like how far on the first and last plate they are. Like for Will, he's really tall, so he actually hits most of the plates really well. But when Tim was walking out earlier, he was actually sitting more on the back end of the treadmill and hit more of just these two. So that's something what we were thinking about doing is maybe like color coding or like coloring the section on the treadmill so people know where they need to walk. And yeah, that's what we're going to do more with software, is trying to figure out exactly how we'll take this data, but this is kind of just, I guess, the initial working patterns.
Were you asking more about like left and right leg specifically?
Kind of, yeah, I guess just saying like the force going through one leg, where it looks like your total graph is the total force on the treadmill, but if you have both feet hitting at the same time, you can't tell what force is going through which leg very easily.
One thing you could do is, I guess you could like videotape the person walking and just put them side by side with the graph and just watch. And then you could do some correlating to that 1 foot walking. And it is different based on each person, because some people have different, like the way they step is a little different for each foot and how long one foot is in the air versus another person. So probably one good way to do it was like videotape at the same time you're recording data or something like that.
Okay, I guess we'll have to cut it off there because we're already a couple of minutes over. Thank you so much.